So, all week we've been looking at reducing radicals, right? And the first 2 days was really just looking at something like this, radical 12, and we just had a very basic thing, and we had learned that we need to break it up into two radicals, with one of them being a perfect square. Then I can take the square root of the one that's possible to take the square root of, and leave the other one alone. So now this, what we did in the first few days, is all embedded within these bigger multiplication and division problems. So that was the first of 3 different rules you've learned. Okay? Just reducing a radical by itself. Okay? The next thing was, what about variables? Okay? So we did square root of m squared, and we did square root of something like m to the 4th. We said all you need to do is divide the exponent by 2. Okay? So 2 divided by 2 is 1, you get m to the 1. 4 divided by 2 was m to the 2nd. Now with odd exponents, you need to have absolute value. With even exponents, you don't. These are just the ones that are on the outside of the square roots. So that was the second rule we looked at. Okay. Third rule was the rationalizing denominator. Third rule says no radicals ever in the answer of these problems. And we said if we multiply, if we have like a single term on the bottom, if we just multiply it by the radical part, top and bottom, okay, then by multiplying these together, they cancel out, the radical cancels out, and this equals 5. Really, it's root 5 times root 5, which is root 25. The square root of 25 is 5, but we don't really need to put that middle step. We just know they're the same thing inside, the same radicands, okay, exactly, then the answer will just be whatever it is inside. On the top, it's okay to have a radical. Okay? And as always, reduce everything fully. So sometimes we might have something that can cancel out. Maybe it's 10 over 4, but there's always something that might cancel. Sometimes it does, sometimes it doesn't. Okay? So those were the 3 rules. Simplifying, okay? Simplifying the variables, and then the idea of no radicals in the denominator of any answer. Most of your work lately has been on this third rule. These are just kind of embedded within them. So when you need to reduce, you just reduce. If it can't reduce, then it can't reduce. You might use it, you might not. We went through a few of these. We said about the canceling. If you have 2 rational numbers, like numbers without square roots, those can cancel. Okay? But if you have the same number that is in the radical and not in the radical, such as number 7, okay, you are not supposed to cancel these out. Why not? Because this one actually is 3. But this square root of 3 right here, the square root of 3 is about 1.7812. We're really just writing square root of 3, so we don't have to write out this decimal. So 3 does not cancel out with this decimal, right? So it's kind of weird to think about, but we have to look at this 3 right here and say, this is 3. This stands for 1.7812. We just don't want to write this decimal over and over, so we leave it as square root of 3. So these do not cancel out. So if they are both on the outside, they're both rational, they cancel out, like we did over here on the 5. Those cancel out for sure. But if one's on the inside, one's on the outside, they don't. And somebody else asked, what if they're both on the inside? Can these cancel out? And the answer was yes. So this x can cancel with this x. Okay? Because they're both on the inside of radical. They're both the same type of numbers, but both irrational. Same thing down here. Both these x's are in the inside of the radical. So they're both irrational. We can cancel those 2 x's out. Okay? So there's 2 y's on the bottom. Cancel those out. And there'll be 2 y's left on the top. So that is okay. As long as it's the same type of number, both on the inside, both on the outside, they do cancel. Then we got to the back. We said, we have the same type of issue. We have radicals in the bottom. Simplify, reduce any radicals that are possible. We can't reduce radical 2, we can't reduce radical 13. So you just go right into your normal routine, that well, radical on the bottom, let's multiply by radical 13. Only thing kind of different here is that you had to distribute the top. Other than that, it was the same. So we had 2 times radical 13. They're different types of numbers, so I just write 2 radical 13. 3 rad 2 times radical 13. Notice how I'm going to multiply just the 2 irrational parts together. So that 3 just kind of comes over. Minus 3, not going to change. This is irrational numbers, you have to multiply those together. Always with the same type of number. So you can cancel the same type of number, you can multiply the same type of number, they have to be the same. So we get 26. And on the bottom, we know that this equals 13. There's already a 3 there, so that equals 39. And we had to be comfortable with this answer. So our answer is quite large. There's a lot of stuff. There's some 2-digit numbers, quite a few of them. We have to be okay with this and not say, oh, I should cancel 13 and 39, I should cancel the 3, I should cancel. Okay, so the canceling does not work when you're adding and subtracting. So I gave this example of 2x over 2 and 2 plus x over 2. And I said, well, you should get the same answer whether you use the shortcut or not of canceling. So like on here, if I plug in 3, I get 2 times 3 over 2, so 6 over 2, which is 3. Do you get the same answer if you just cancel? These out. Yeah, you get 3. So it's okay to cancel when it's multiplying. But over here, what happens if you plug in 3? You get an answer of 5 over 2. That's 2.5. Do you get that same answer if you just cancel the 2's out? No, you get 3. So canceling does not work with adding and subtracting. So it's the same argument as, do 2 negatives make a positive? Right? Do 2 negatives make a positive?
No. Yeah.
Yes and no, sometimes. Multiplying and dividing, like right here, 2 negatives make a positive. Adding, subtracting, -2 plus -3. Do these 2 negatives make a positive? No, it equals -5. 2 negatives make a negative. So we have to be able to switch back and forth between rules. If we're multiplying, dividing, yes, we can cancel. If there's any adding, subtracting, then you cannot. Okay. So same idea, we have to separate the rules. So on the back side, there was absolutely no canceling going on. Okay. There will be a little way to reduce some of the problems later. But right now, we're not going to just say, oh, same thing, top and bottom, all cancels out. That is not true. As always, when we got to here, before we did anything, we had to reduce a radical, so we're still going to do that. So don't just automatically see a radical on the bottom and say, multiply by a radical 20 top and bottom. If it can be reduced, always do that first, and then the last thing you'll do would be to rationalize. Okay? So we don't want to multiply by root 20 top and bottom. You want to multiply by just root 5. And of course, don't forget parentheses and distribute. The last thing we looked at, the very last thing we looked at yesterday was down on number 20. And I wrote this out and I said, well, we got to get rid of a radical on the bottom. And I did this. Okay? So if I multiply this by root 3, it should cancel out the radical, right? But here's the problem. We had to distribute it. So doing this doesn't really work. When I distribute, I get 3 rad 3 minus rad 3 times rad 3 is just 3. You see that multiplying by this did not solve the problem of getting rid of the radical denominator. Yeah, I got rid of this radical, but it created another one right here. So this method of just multiplying by the radical and only the radical does not work when you add adding and subtracting on the bottom. Okay. So instead, I mentioned this. 3x plus 2 and 3x minus 2. What does this equal? There was something special about having the exact same terms, right? And one positive, one negative. There's something special about that. And that is that we didn't really need to use the box. We knew that the middle terms were going to cancel out. And then positive times a negative is negative. And it went the other direction too. If I had 16x squared minus 81, I didn't even need to use the x. I didn't need to use the box at all. I knew that, well, this is a perfect square, if this is a perfect square, if subtraction, it's just going to be 4x and 4x to make 16x squared. It's going to be 9 and 9 to make 81, and then positive and negative to make the negative. So we're using this idea that, well, we can cancel things out if we just have the exact same thing, but we change the sign. We have to have one positive sign and one negative sign. And since this is the negative sign, we go ahead and multiply it by positive. Notice how it's just the sign between the terms. It's not like I don't need to change anything else. And we had to do this on the top and bottom. And by doing this, similar to here, where I can just say, okay, this is 3x times 3x is 9x squared, 2 times 2 is 4, negative times, a positive times negative, negative. I can do the same thing here. I don't have to use the box. I don't necessarily have to use the x. I can just go ahead and say 3 times 3 is 9. Root 3 times root 3 is 3. And then negative times a positive is negative. So I know my denominator is going to be 6. And of course, the top we have to distribute. Don't forget parentheses. 6 plus 2. My final answer is 6 plus 2 root 3. Okay. And for now, we're going to leave that as our final answer. I'm not going to cancel. The 6's don't cancel. The 2 and 6 don't cancel. You cannot cross them off because of this addition. If that was multiplication, we can cross everything out, reduce it. But with the plus sign there is no reducing. So often I'll see on quizzes, like the ones you're about to take at the end of the period today, I'll see the right answer. And then people keep on doing stuff, and they'll come up with something like 1 plus root 3, because the 6 cancels here, and they'll come up with some other reason to do more. Most of that comes from not being comfortable with having this much stuff as your final answer. That belief that everything should just be reduced down to something small and neat. But in actuality, that's as far as we're going to go. Okay. So on all of these, you had to go through and multiply by what was called, to make this work with one positive and one negative, okay, it's called the conjugate. So the fact that I'm changing just the sign in between, it's the conjugate. So we had to go through and change each one of them. So it's 16. See if you can reduce any of these radicals, right? You can. So we had to go through and multiply it by negative 5 minus 5%. Same thing on top and bottom. Notice how just the sign between the numbers, the negative 5 and the front is still exactly the same. I'm changing just that. Alright, we can multiply these together. Negative 5 times negative 5 is 25. 5 times 5 is 25 again. But then we have root 5 times root 5, which is another 5. Positive times a negative is a negative. So we end up with 25 minus 125, which equals negative 100. So my denominator here is going to be over negative 100. So that last part, just think about what we're actually doing here. It's not so bad. I know what 5 times 5 is, that's 25. I know root 5 times root 5 is 5. I know 25 times 5 is 125. And I know that 25 minus 125 is negative 100. So each of those one little steps by themselves is basic arithmetic. Nothing we don't. We just have to make sure we do it in the right order and we don't skip anything. So I color code this. I got that. I got the rationals, that's these. That's where this 25 came from. And then I have the irrationals, so radicals. That's where that 5 came from. Now notice how this is all one term. This is all one term, right? That's why I'm multiplying these two answers together and getting 1.1. So I want you to spend a little bit of time, about 10 minutes or so. Look back over all these problems on the backside. Finish anything that's not finished. Not collected if it's finished by 10 minutes. If you're finished, make sure your definition of finished is my definition, meaning you have 100%. So I could grade it and nothing would be wrong. Your definition, if your definition is I wrote something last night, so I'm done, I'm going to sit here and do nothing, that's not finished. That's you wrote something. That's building a car and then not turning it on to see if it actually works. Or building a car and then turning it on and find out, well, it does everything but go in reverse. It's almost correct. It's almost right, but I'm just missing one thing. And then saying, oh, well, I guess that's the way it is. So even if you wrote something down, you keep checking until you know it's 100% correct. Even furthermore, you're taking a quiz on this right now. Make sure you know how to do it. Don't get the right answer. Oh, somebody else did it next to me. Let me write it down and then take a quiz and fail. If you try to lie, cheat, take shortcuts, this is what happens. You don't pass math classes. If you honestly spend the time trying to figure out how to do it, asking questions, helping each other out, you will learn how to do it and you'll be fine. Okay? So keep that in mind. If you're sitting there saying I'm done, would you bet $1 million that everything's 100% correct on your paper? The answer is no, you're not done. That's not being done. Okay? All right, so go ahead and do that. I'll be around to answer questions.